IP functions as a best effort delivery system. A sender transmits a packet, and the protocol makes its best attempt to reach the destination, but it provides no inherent guarantees and no default feedback. When a packet is lost in a routing loop or dropped by a firewall, the sending device remains unaware of the failure. The sender simply waits until an application layer timer eventually expires. The TCP/IP suite addresses this lack of visibility through the Internet Control Message Protocol, or ICMP. It acts as the diagnostic sensor for the network layer. ICMP generates error reporting and diagnostic data regarding how IP packets are processed as they traverse a network. As this graphic illustrates, ICMP provides feedback about problems rather than a reliability guarantee. It allows a stateless protocol to function at scale by providing the data required to troubleshoot processing issues. ICMP functions as the underlying engine for network discovery, powering the diagnostic tools, like ping and traceroute, required to maintain a modern internetwork. The protocol is divided into two versions, ICMP v4 and ICMP v6. While they share similar diagnostic goals, their operational roles on the local link differ significantly. Mastering ICMP is the key to moving from blindly sending data to intelligently troubleshooting the path it takes. The most basic diagnostic mechanism in the suite is the test for host reachability. The process begins when a local host queries a destination, sending an ICMP echo request, represented by the green arrow. If available, the target responds with an echo reply, the blue arrow confirming the return path. This specific exchange provides the structural foundation for the standard ping utility. Ping calculates the round-trip time between the request and the reply, offering an immediate measure of network performance and latency. Troubleshooting follows a logical outward progression. As shown here, you first ping the loopback to verify the local stack, then the gateway for local connectivity, and finally the remote host to test the entire internetwork. A successful ping confirms a valid path exists. However, its absence only indicates a failure has occurred. It does not pinpoint where the breakdown is located. In IPv6 environments, ICMP handles operational tasks that previously required separate protocols, such as dynamic address allocation. This is part of the neighbor discovery framework. In the left column, we see the specific messaging types used to manage communication between routers and devices. When an IPv6 host boots up, it broadcasts a router solicitation message to locate its local gateway immediately. The router responds with a router advertisement. As this table shows, the RA message contains the network prefix length and the router's link local address. Hosts use this data to perform stateless address auto-configuration, or SLAC. This allows a device to configure its own global address without a central DHCP server. This two-step sequence is the initial boot-up exchange. To keep devices updated, routers also transmit these RA messages periodically, every 200 seconds. This ensures that for IPv6, ICMP is a functional necessity for basic network membership rather than an optional diagnostic. ICMP v6 also manages the resolution of MAC addresses. When a host knows a destination's IPv6 address but lacks its hardware address, it initiates a discovery process. The host sends a neighbor solicitation, the blue arrow, to a specific multicast group associated with the target address. The target device replies with a neighbor advertisement, shown by the green arrow, which reveals its MAC address to the requester. This same mechanism provides a critical security and configuration check called duplicate address detection, or DAD. A host pings its own newly assigned address using a neighbor solicitation. If it receives a response, as seen in Outcome 1, the address is already in use. If no response arrives, as in Outcome 2, the address is confirmed unique. This initial resolution process is often why the first ping in a new troubleshooting session times out before subsequent requests succeed. These NS and NA messages unify local discovery under the ICMP v6 umbrella, effectively replacing the legacy ARP protocol used in IPv4. Shifting to multi-hop routing, we have to examine what occurs when a packet encounters a failure mid-path. This section of the source highlights destination or service unreachable messages. This provides the primary conceptual feedback loop for packets that cannot be processed. When a router receives a packet it cannot deliver, it discards the data and sends an ICMP message back to the source explaining the failure. These codes offer high precision. As the table indicates, a code 0 suggests the network itself is unreachable, while a code 1 indicates the path was blocked by a security feature like a firewall. This feedback is also critical for managing routing loops, where misdirected packets might otherwise circulate endlessly. To prevent this, every IP packet includes a safety counter, time to live in IPv4, and the hop limit in IPv6. Each router along the path subtracts one from this field. The TTL decremented labels here show that counter ticking down at every hop. When the counter reaches 0, the router drops the packet and transmits an ICMP time exceeded error back to the source. This mechanism is a critical safety feature that prevents a network from collapsing under the weight at infinite traffic loops. By intentionally triggering these time exceeded errors, we can map the exact path a packet takes through the network. The traceroute utility leverages this time exceeded mechanism to perform network topology mapping. The tool sends a packet with a TTL of 1, which expires at the first router, returning an error recorded as hop 1. It then sends a packet with a TTL of 2, surviving the first hop but expiring at the second, revealing hop 2. By incrementally increasing the TTL, the tool methodically identifies every router interface along the entire communication path. The process concludes when the packet reaches the target host, which responds with a standard echo reply instead of an error. This resulting table provides the IP address and round-trip time for every individual hop. Spikes in these values allow engineers to isolate specific points of congestion. While ping confirms that a path exists, traceroute reveals the specific topology and pinpointing the location of network failures. ICMP provides the indispensable feedback loop that makes IP networks manageable and diagnostable. It powers fundamental diagnostic tools like ping and traceroute, and handles the mandatory link layer discovery required for IPv6 to function. However, because ICMP reveals detailed internal data, network administrators often block it at the corporate perimeter for security reasons. This means an asterisk in a trace or a failed ping does not always indicate a broken path. It often identifies a secure network policy. Mastering the mechanics of these messages is the difference between a technician following a script and an engineer who understands the fundamental logic of the network.